This video is about forces and braking, which is an important piece on the physics and trilogy specifications. The specification states that the stopping distance of a vehicle is the sum of the distance the vehicle travels during the driver's reaction time, the thinking distance, and the distance it travels under the braking force, called the braking distance. For a given braking force, the greater the speed of the vehicle, the greater the stopping distance. And if you're studying physics, you need to be able to estimate how the distance for a vehicle to make an emergency stop varies over a range of speeds typical for that vehicle. And also you'll be required to interpret graphs relating speed to stopping distance for a range of vehicles. As a starter activity, you could now stop this video and watch the demonstration that's done at this web address. This is done in New Zealand, where they do their speeds in kilometers per hour. So I've done the conversions there to miles per hour. The specification stated that the stopping distance was the sum of the thinking distance and braking distance. So written mathematically, that is, the stopping distance equals the thinking distance plus the braking distance. And quoting that is an easy mark if it comes your way in a question. I simply have to state that little equation. Now it's essential you understand the definitions of these two terms. So first of all, the thinking distance, that's the distance the vehicle travels during a driver's reaction time. So it's the time between seeing a hazard and applying the brakes. The braking distance is the distance the vehicle travels after the brakes are applied before it comes to a complete stop, and that would be as a result of the braking force. Now many students make the mistake of stating that the thinking distance is measured in seconds. That's because they're used to reaction time. Now reaction time is in seconds, but thinking distance has got to be expressed in meters. It's the distance that the car travels while you are thinking about reacting. So in the British Highway Code there are a table of typical stopping distances, and if the hazard is closer than the distances shown for that speed, there's likely to be a collision. Now I've deliberately here taken three speeds where I've gone 20, 40 miles an hour, so I've doubled it, and then I've gone 60 miles an hour, so I've tripled it for the original speed. Now if you have a quick study of those distances, the component parts of the blue thinking distance and the red braking distance, you may be able to see some patterns. So you could pause the video here for a moment, have a look at those numbers, see if you can spot the relationship, and I'll cover that on subsequent slides. So you may have noticed that if I double the speed from 20 miles an hour to 40 miles an hour, that's from 9 meters a second to 18 meters per second, then the thinking distance also doubles. So that's gone from 6 meters to 12 meters. However, if we look at the braking distance, doubling the speed from 9 meters a second to 18 meters per second doesn't double the braking distance. It doesn't go from 6 meters there to 12 meters. It goes up 4 times to 24 meters. So if you double the speed, you get 4 times the braking distance. And it might be worth here realizing that 4 is 2 squared. So if you double the speed, you've 2 squared times the braking distance. So having got that relationship there, and I've repeated the 9 meters a second and 18 meters per second there, what would be your thinking distance, braking distance and overall stopping distance for a vehicle going at 80 miles an hour? Pause the video for a moment and see if you can work out what those would be. So hopefully you'll have taken your values for the 40 miles an hour. You'd have taken your thinking distance of 12 meters and you will have doubled that because you've doubled the speed to 24 meters. You'll have taken your braking distance of 24 and multiplied that by 4 because it goes up by 2 squared. So that will give you 96 meters. And if you add those two together, it will give you a total stopping distance of 120 meters. We're going to try and understand now the relationship between the braking distance and the speed. So first of all, we're going to look at how the braking distance is related to the kinetic energy of the car. Now we know that kinetic energy equals half the mass times the speed squared. The mass of a small car would be about 1,000 kilograms. So if the car is going at about 30 meters per second, then our kinetic energy would be half times the mass, that's a half of 1,000, 500, multiplied by the speed squared, 30 squared, so that's 900. If we multiply those, we will get 450,000 joules. Now if the car is going half that speed at 15 meters per second, then the kinetic energy is still half times the mass, 500, but this time multiplied by 15 squared. That gives us a kinetic energy of 112,500. And you will notice if you take the second of those and multiply it by 4, you get 112,500 times 4 gives you 450,000. So our speed has decreased by a half from 30 to 15, but our energy has decreased by a quarter from 450,000 to 112,000. So straight away we're getting that relationship that one is doubled, the other one is doubled squared. So now let's relate the braking distance to the force. Now we know that work done equals force times distance. Work done is also the energy transferred, and in this case we have got the energy is transferred from the kinetic store of the car to the thermal store of the brakes and the tyres. Now the car's brakes exert the same force whatever speed you're going. So we're going to take that as being 2,000 newtons. If our car is going at 30 meters a second, we know its kinetic energy is 450,000 joules. We rearrange the equation to distance equals work divided by force, 450,000 divided by 2,000, giving us a distance, and that's our stopping distance, of 225 meters. If our car is going at half the speed, at 15 meters per second, we know its kinetic energy is a quarter, that's 112,500 joules. The distance we work out is the 112,500 divided by the 2,000, and that gives us a stopping distance of 56.25 meters. You'll notice that the stopping distance has gone from 225 to 56.25. It's gone to a quarter of the stopping distance, whereas the speed has gone from 30 to 15, so it has halved. So here's a straightforward example. A driver sees a hazard on the road and brakes. Its thinking distance is 11 metres, braking distance 32 metres, find the stopping distance. And you simply apply the equation. Stopping distance is the thinking distance plus the braking distance, 11 plus 32, giving you a stopping distance of 43 metres. So this will be for physics students only. To have a look at a graph, something like this, and to make some conclusions, to make some comparisons. So first of all, I've asked you to compare the thinking distance for both a car and a lorry, and to explain those. Then to compare the braking distances and explain. And then a final question there asking, why do you think lorry drivers have to do an additional driving test? So pause the video here, have a go at those questions, and then I'll go through some answers with you. So hopefully you'll have noticed that the thinking distances for the lorry and the car at particular speeds are exactly the same. And the reason for this is that if you've got the same driver driving a car as a lorry, their reaction time is going to be the same in both vehicles, and therefore the distance their vehicle travels in that time will be exactly the same. The braking distances. You'll have noticed that with the braking distance for the lorry is more than that for the car. Reason for this would be that the mass of the lorry is much greater than the mass of the car, and therefore it takes more force over a larger distance to convert, so transfer that kinetic energy into thermal energy in the brakes and the tyres. If you actually get a ruler and measure the length of the bars, you'll find that for the first ones, the braking distance is about twice as much for the lorry as it is for the car. For the third one, it's just under twice as much. So you could say in an exam that the braking distance is about double for the lorry compared to the car. The final question there about lorry drivers having to do an additional driving test. They have to do this extra driving test partly to appreciate the difference that the extra mass makes to their braking distance. They have to be much more forward thinking and read the road in a different way to if they're in a car. This is the AQA specification for reaction times. You're expected to know that reaction times vary from person to person, and the typical values range from 0.2 seconds to 0.9 seconds. A driver's reaction time can be affected by tiredness, drugs or alcohol, and distractions may also affect a driver's ability to react. In particular, you should be able to explain methods used to measure human reaction times and recall typical results. You should be able to interpret and evaluate measurements from simple methods to measure the different reaction times of students, and also to evaluate the effect of various factors on thinking distance based on given data. So the stopping distance is made of two components, the thinking distance and the braking distance. And first of all, we're looking in detail at the thinking distance and the factors that will affect that distance. The thinking distance is affected by two main factors. First of all, how fast you're going. So we've said before, whatever your reaction time, the faster you're going, the more distance you'll cover before you respond. And then the second factor is how quickly you respond. In other words, your reaction time. And that itself can be affected by factors like tiredness, drugs, that would be legal or illegal, alcohol, lack of concentration, and distractions. And you are expected to know that typical reaction times are between 0.2 and 0.9 seconds. Of course, during that time your car will be continuing to move, and therefore we have the thinking distance. Now, in completing this table here, where you're looking at different factors, the effect on the thinking distance and an explanation, you may use some ideas from your biology GCSE, particularly in terms of the transfer of impulses along neurons and the transfer across the gaps between neurons, which are called synapses. So do use those ideas you've got from another subject in your physics if you're explaining something to do with reaction time. Now do pause the video at this point and have a go at the experiment about reaction times. You'll need a partner. The instructions are given you on the other YouTube produced by our department. And the suggestion at the end is that you think about how you could use the method to assess some of the factors that were in the table in the previous slide. If you're doing the higher paper, it is possible that you could just be given a distance for a ruler dropping and be expected to work out the reaction time. If you have this, this will be a two-part calculation where you're using one equation to work out the speed that the object will be travelling, and a second one where you'll be working out the time it took during that motion. So the example here is you've got to catch a ruler and you catch it at 25 centimeters. So you convert that to meters, 0.25 meters. You then find the final speed of the ruler. So given acceleration due to gravity is 9.8, your distance is 0.25, and u squared, so that's the initial speed squared, is 0. So our equation becomes v squared is 2 times 9.8 times 0.25, giving you 4.9, and then you need to find the square root of that, giving you 2.21 meters per second. You then insert that speed into the second equation, which is acceleration is change of velocity divided by time. So we know the change of velocity is 2.21 meters per second. We know the acceleration is 9.8. So rearranging the equation, we will get the time is the velocity divided by the acceleration, change of velocity divided by the acceleration, 2.21 divided by 9.8, giving you 0.23 seconds. And we said before that normal reaction time range is between 0.2 and 0.9 seconds. So here is the syllabus for braking distance. The braking distance of a vehicle can be affected by adverse road and weather conditions and poor condition of the vehicle. Adverse road conditions include wet or icy conditions, and poor condition of the vehicle limited to the vehicle's brakes or tyres. And you should be able to explain the factors which affect the distance required for road transport vehicles to come to rest in emergencies and the implications for safety. So we've put the braking distance factors into 4 here. So first of all, how fast you're going. The faster you're going, the further it takes to stop. How good your brakes are. So if they're worn out or faulty, they won't apply as much force and therefore make it harder to stop. How good your tyres are, that's your third one. Well, tyres should have a minimum tread depth of 1.6 millimeters. Don't have to know that, but you do as a driver. The greater tread means greater friction. So when the brakes are applied, there is a greater friction between the tyres and the road to bring the vehicle to a halt. And then also to do with friction, we have number 4, how good the road surface is. So comparing wet or dry, icy, loose chippings versus a hard surface, and each of those will affect the friction between the tyres and the road. So for example, a wet surface will reduce the friction between the tyres and the road, meaning there will be a longer stopping distance due to that smaller amount of friction. So pause the video here and see if you can fill in this table here, where you're given 5 factors and you're being asked to give the effect on the braking distance. So we want whether the braking distance will be greater or smaller, and then an explanation for that. In your explanation, you'll need to be using physics concepts like force, maybe the transfer of energy, friction, and so on.